All right. Again, thank you for your patience. I have a ticket filled out that, well, they're going to come tomorrow and hopefully it's my computer. If not, I'll have to reload all of the meetings and then we'll get it to work. But we've accomplished our review. I will post that video so you can go back and watch it. Today's lesson, we're going to start the next topic, ocean water and its chemistry and the properties of water. The issue seems to be when I share my screen, I cannot get back. So what I'm going to do is I'm going to share my screen right now, and then I'll dismiss from the PowerPoint screen. So this will be the last time you see my smiling face this lesson, but we will cover all of the information that we need to cover. And then I will have the techies come and see what's wrong with our computer and hopefully get everything ironed out. I just need to remind you, and I threw this on the PowerPoint because I haven't been able to switch screens but one time while I was logging in. That's probably why it took a couple of extra seconds, but the second thing that's due after the quiz this week is your current events review of 2 articles. Similar to the first one you did, I don't need peer-reviewed science articles. I would prefer what normal people would read because the goal of this class is scientific literacy. So things like National Geographic or Discover are every bit as valid as a scientific journal in this case. And again, you put things in your own words. If you take a direct quote, go ahead and throw quotes and then put in the bibliography. You're going to want the cover page, the title, and the author. You're going to do one for each article. So you would have a paragraph on the article, and then a paragraph describing your position or experiences or conclusions or what you learned from the article. So 2 paragraphs per article. And that is basically what we're looking. Now, this topic is exploring the seafloor for natural resources. So you could talk about oil drilling or the hydrates, or mining the seafloor for minerals, any of the natural resources that we discussed in class. You could look at it from how much money's made or how it's extracted to the environmental damage. I'm not going to tell you what tack to take or what articles to pick. There should be an abundance of articles discussing gas or petroleum or natural resources, minerals, anything along those lines in your search. And so that is it kind of goes with our topic of the seafloor for this unit. And make sure you have a cover page. It can be on 1 page or 2 page, it really doesn't matter to me. And then lastly, you're going to want to have your APA reference page at the end. So that is also due Wednesday along with the quiz. So you have 2 things due Wednesday. Now today's lesson, we're gonna just break in water. It's a 2-parter. So we're gonna get through part of the presentation today and then continue with it on Wednesday. Take a look at this image. In a former life, I was a underwater photographer, scuba diving, dive master. It was a lot of fun. I didn't do it for a living. I was more of an amateur as I collected samples and images for personal use and for scientific use. And also I've been published in the newspaper a few times, things like that back in my youngin' days. One of the things that you learn as an underwater photographer is light attenuation. Attenuation is light is lost as you go at depth. It's lost by frequency. So the lower frequencies, the reds, filter out first. And then you get the Roy G. Biv. So the blue, the indigo, and the violet penetrate the deepest. So as you go deeper, things become more blue and less red. So you lose the reds. This is just a shot with a strobe, and you can see all the color, and without a strobe, and you can see the colors are drabber, but they still got a lot of the blues. So within the first 10 meters or so, you lose red, which is this shot here. Look at all the red. So the strobe illuminates the red. Here, you don't have the red light. You don't have the red down here. You just don't get the red. So it's shocking your first set of photos you get back, and there's all this red that you don't remember seeing. And you're like, my goodness, that didn't look like that to me. But that's because we only see what's reflected. And if there's no red wavelength, you don't see the reds. Interestingly, the algae that thrives the deepest is red algae. And that's because there's no red light. You see, the red algae reflects the red light when you pull it up because it doesn't have pigments designed to absorb it because it doesn't exist, red light at depth. So why would you develop pigments to absorb it for photosynthesis? It's just not there. So when you drag the algae up and you look at it, it appears red. And so it belongs to a group of algae. The red algae is called Rhodophyta. And they do the best in the deeper water because they're not, but they don't use red light, where algae that grows shallower has the pigmentation to absorb the red light. So it doesn't appear red because you're seeing what's reflected. So that's light attenuation. Now next class, when we talk about the properties of water more in depth, we're going to look at a light attenuation. But for now, we're just going to keep it simple and talk about what water is first. To talk about what water is, we have to distinguish between atoms and elements and molecules and compounds. So an element is one type of atom. An atom comes from the Greek term atomos, which is evolved through the years. The ancient Greeks would say they're tiny little balls of matter that make everything up, all the way through Dalton's theory of matter. That was the prevalent thinking. And then people like Rutherford performed experiments and discovered subatomic particles made up atoms. So atoms, the smallest part of an element that you can't really separate an atom by natural means. You can split the atom, and use unstable isotopes, but atoms themselves, the element is defined by the number of protons of that atom. So all carbon have 6 protons. If you have 6 protons, you're carbon. If you have 8 protons, you're an oxygen. 1 proton, you're a hydrogen. 2, you're a helium. So the element is defined by the number of protons in the atom. And then a whole bunch of helium atoms is considered the element. Some elements are stable. Other elements are very reactive, and they don't really exist elementally in nature. Take, for instance, oxygen. Oxygen is very reactive, so it doesn't exist as elemental oxygen. It exists as O2, which is what we breathe in. So oxygen literally reacts with itself. It exists as O3, which is ozone, and it exists in compounds because it's so reactive. It just reacts with everything. Other elements are more stable, and you can find them as elements. So compounds are made of different atoms that are sharing or have transferred electrons. Then you become a compound because you're with something else. So the molecule is a group of that. A molecule is down to the molecular level, or one like a hydrogen, H2O would be a molecule. And then a lot of H2Os would be the compound called water. So as an atom's the smallest part of an element, a molecule is the smallest part of a compound. So through time, like I said, we've developed our models of the atom. The reason we use models is because we can't see an atom, it's too small. So we just have to make models of it based on the way it acts in different situations. And the most common model that we look at, which is not a correct model, by the way, but it's the most common and easiest way to explain the atom, is this Bohr model, or the satellite model, kind of like when you're a kid and you glue all the little styrofoam balls in the middle, and you have protons and neutrons in the nucleus, and then electrons in these orbitals around the nucleus. And it's a neat way of looking at it. Here you have an eight protons, so it's an oxygen, 8 neutrons, and then you have 8 electrons in the orbits. The first orbit's small, it holds 2. The next orbit holds 8. The orbit after that holds 8. And then you start getting into metallic elements with suborbitals and things like that. Now, atoms are reactive when they do not have that full outer energy level. They share electrons or trade electrons, and that's how compounds are made. So an unstable element like oxygen does not have a full outer energy level because it takes 8. So they react with other things to get that full energy level. And that's why chemical reactions occur. So when you look at the protons, they're positive and they're in the nucleus and they define that element. You look at the neutrons, they're neutral. They're found in the nucleus. They vary in number, and that's what makes an unstable isotope. Electrons are very small, negatively charged. They're outside of the nucleus, and they are dynamic. They can be gained or lost to form ions, and that would be an ionic bond, or they could be shared to form covalent bonds, like cooperative, CO, covalent. Valence means outer energy level. So covalent means shared outer energy level. This Niels Bohr model of the element, it serves our purpose. It's not as accurate as you get into higher level chemistry, but it does make it easy to explain chemical bonding, so we run with it. Really, atoms are far more complex, like this image shows you, where you have a cloud of electrons and a nucleus, and these electrons can be found in different shaped orbitals. So it becomes rather complex when you learn wave dynamics, but we're not covering wave dynamics in this class, so we're going to keep it with the satellite model to help explain hydrogen bonding, covalent bonding, ionic bonding, and the properties of water. So I mentioned the 2 types of chemical bonds. The first type are called ionic bonds. The second type is called covalent bond. Ionic bonds form when electrons are gained or lost. If you gain electrons, you become a negative ion. When you lose electrons, you become a positive ion. Negative and positive attract each other electrically. So the ionic bond is the attractions of oppositely charged ions. Something like oxygen that only needs 2 electrons to fill its outer shell will receive electrons and be a negative ion. Something like sodium, which has 1 electron in the outer shell, likes to lose electrons, and that will become a positive ion. So ionic bonds form when elements that lose electrons are transferred to elements that gain electrons. The compounds they form are called salts. So a salt is formed by ionic bonding. Here's the most common salt. You have sodium, which has 1 electron in its outer shell, chlorine, which has 7, and like we said, the magic number is 8, so the electron is transferred from sodium to chlorine. So sodium becomes a positive ion. Here's a little sodium ion. Chloride becomes a negative ion. Here's a little negative ion. They attract, forming grains of salt. So salt, sodium chloride, is a type of salt. It's the most common type. It's what we use as table salt. But there's other salts as well, are when elements that lose electrons, which we call metals. Metals lose electrons. That's why they conduct electricity. Electricity is the flow of electrons. They lose electrons to a non-metal, forming, the metal forms a positive ion. The non-metal forms a negative ion. They then are attracted to each other, forming a salt. When they're not in water, salts take a crystal form. We're going to learn shortly that water is a polar molecule. A polar molecule means it has a positive charge on one side and a negative charge on the other. And because it's polar, it dissolves solids that have polar properties like a salt. So sodium chloride, salt, dissolves in water because the water is polar. And oil is nonpolar. So oil does not dissolve in water. That's why oil floats on water, because oil is nonpolar, does not dissolve in water, and it's less dense than water, so it sits on top of water. So you have ionic bonding, and ions dissolve in polar substances. Water is a polar substance, and we call water the universal solvent because polar substances dissolve in water. Covalent bonding are when electrons are shared. This image right here, this image, make it a little bigger, that is methane, our simplest natural gas. We mentioned natural gases. Methane's the smallest because it only has 1 carbon. And ethane has 2, and butane has 3. So the more you add, it changes its name. So this hydrocarbon, hydrogen is sharing an electron with carbon. So now carbon has a full outer shell, hydrogen has a full outer shell. So you have a molecule. The covalent bond are when atoms share their outer electrons. This would be a nonpolar covalent bond because all of the sides are shared equally. Now, water is a polar covalent bond. Here's a water molecule. There's your oxygen. Here's your hydrogens. Oxygen pulls stronger than hydrogen. So oxygen takes on a little negative charge. Hydrogen, which can't hold the electrons as well, takes on a little positive charge. So they don't share evenly. It's like if you were to share candy with your little brother and you broke it and you had a big piece and a small piece, you keep the big piece for yourself and you give the small piece to your little brother. That's uneven sharing. So oxygen does not share evenly with its hydrogen counterparts. So they have a pole. The oxygen takes on a negative, the hydrogen takes on a little positive. And in this case, hydrogen bonding, it's not really a bond. It's actually a van der Waals force because a scientist named van der Waal was the first to describe it. It's an attraction, a partial bond, if you will, between, in this case, the 2 water molecules. This is one of the most important concepts in water chemistry, this hydrogen bond, because the hydrogen bond makes water a liquid. The three states of matter, solids, the elements, the atoms or molecules are tightly packed. Liquids, they are associated with each other. And gases, they basically move around and have an occasional collision, but they don't have anything to do with one another. So the liquid here, that allows chemical reactions to occur. Solids are a little too tight in their lattice for good chemistry. Liquids don't really, gases don't associate with each other as well, so they're not great for chemistry. Most chemistry happens in a liquid because they are in close proximity, but still free to move around. So water is the basis of life because of its chemistry. Water is such a small element or molecule. Oxygen is not really a large element. Hydrogen is the smallest element there is. So by cell mass or by atomic mass, it should be a gas, but it's held in a liquid form because of this hydrogen bonding, and that allows for water's unique properties. What are some of water's properties? High boiling point. Takes a lot of energy for water to turn to a gas. So naturally on Earth, water can turn to a gas via evaporation because it's so small, just at the surface, a molecule at a time, but then it condenses and falls back to Earth as a liquid. So because it's light, we have a water cycle, but because of hydrogen bonding, we have liquid. Water is less dense as a solid because of that hydrogen bonding, because it lines up as a crystal. So we have ice, and ice floats on water. If ice didn't float, then everything would die every time something froze. The ponds would freeze from the bottom up. The ocean would freeze from the bottom up. It would be impossible to have life in the Arctic. So it's very important that ice is less dense than water. That's because the airspace in the ice, because the water molecules line up in a crystalline structure. Water has a high heat capacity. That's how it moderates world climate. It absorbs the energy from the sun and heats up slowly and cools off slowly, where land heats up and cools off quickly. So climate is stabilized on Earth because we're mostly water. Water sticks to itself, like this illustration here showed. That's cohesion, or it sticks to any other polar surface. That's adhesion. Your hair gets wet because it has tiny charges and the water sticks to it. The more curly hair you have, the more hydrogen bonding your hair has, and the wetter it gets, and it stays wetter. If you were to say wax your car, you're applying a non-polar surface. That wax, which is non-polar, it's an organic non-polar. You spread it on your car, and then the water hits it and slides off it. So you wax your car to keep the water from building up on it, because water has dissolved salts and dirts. So if water stays on your car and it evaporates, it makes your car dirty. So basically wax is applied to cars to let the water roll off before it can evaporate and keep your car clean longer. Keep it all shiny and nice. So water has a lot of properties. Capillary action. Water moves up a tube. Trees utilize that because trees don't have hearts. They can't pump water. But water moves up through them by capillary action because it's charged. It moves up a charged tube. Water has surface tension. If you've ever done belly flop, you know that at the surface it lines up, forms a thin skin. This water strider cruises along on top of it. So water has a lot of unique properties because of hydrogen bonding. Non-polar waters do not, or non-polar molecules do not mix on water. So here in any marina, you'll see oils, gases, or whatever floating on top because it's less dense. So the heat and temperature, water absorbs heat very well, does not change temperature, moderates climate. The units of heat are calories. Yeah, and we know calories in food as well. And how you get your calories on food is it's burned, and the amount of energy given off is measured in calories. Generally speaking, they put it in a box of water and burn it and then measure the temperature change of water. So a calorie is defined as the amount of heat it takes to raise water 1 degree Celsius. A gram of water would be a small calorie, and a kilogram of water would be a large calorie, that capital C, or a kilocalorie. So the change in water temperature is what we base the units calories on. Calories is how we measure heat. And because you eat food and you burn it, quote unquote, burn it, metabolize it actually, for energy, that's how we measure the caloric intake of food as well. So water changes temperature very slowly. It takes a lot of energy to change temperature because of hydrogen bonding. It's hard to get those water molecules to vibrate because they're held in place by those attractions. And water has the high specific heat. So calorie is the measure of the unit of energy. A small calorie with a small c is 1 gram of water. A capital, or more often kilocalorie, is 1 kilogram of water, 1 degree Celsius. And we call this the amount of energy it takes to change change 1 gram. We call that the heat capacity. Water is the index of 1. And look, granite and sand, which makes up most of our continents, 0.2. So really, it heats up 80% faster and cools off 80% faster land than water. That is super important when it comes to world climate. When we talk about climatology, we'll learn more about that. We mentioned states of water, solid, liquid, gas, and then plasma. Okay, now plasma is kind of an interesting, it takes atoms out of its ground state and jumps electron orbitals, and then as they return back, light's given off. Plasma does not exist under natural conditions. Around severe lightning strikes, instantaneous plasma can be formed. Around in the upper atmosphere, as solar wind glances off of our magnetic field, plasma can be formed in the aurora borealis. Under lab conditions, we can form plasma. It's high energy ionized particles. So we're not really looking at plasma in the ocean realm. We look at the solids, the liquids, and the gases. Solids, again, tightly packed. Gases, a particle will whiz by, not associated with another. And liquids, you can have movement within. So the change from solid to liquid to gas, gas to liquid to solid, we call a phase change. That is the change in state. Same amount of energy to melt and freeze, to condense and boil. It's just positive or negative. So the phase changes would be the heat of fusion and the heat of vaporization. That's what it's called. If it's positive heat of fusion, then you're melting. If it's negative heat of fusion, then you're freezing. If it's positive vaporization, you're boiling. If it's negative vaporization, you're condensing. So substances are given heating curves. That heating curve is drawn out. Here's water's heating curve. You have your 3 states, solid, liquid, gas. You have your melting point, your boiling point. Boiling point is vaporization. Notice you're still adding heat, but the temperature stays the same until all of it's vaporized. You're still adding heat, the temperature stays the same until it's all melted. It takes a lot less energy to melt than it does to vaporize as far as water goes. And this is a heating curve of water. here is what we call each phase change as we move between states. So if you ever see the term sublimation, you're skipping the liquid phase and go straight to gas. And we've heard of melting and freezing and vaporizing and condensing. These are the different phase changes. All right, so the latent heat of fusion, latent means hidden, latent heat of fusion is the energy it takes, right here, the energy it takes to change the state from a solid to a liquid or back. The latent heat of vaporization, again, latent means hidden because there's no temperature change, is the amount of energy it takes to condense or vaporize. The effects that this has on temperature is staggering. You can look at the heating curves here of San Francisco and Norfolk. Now note they're both near water, but the westerly winds blow across. So this has a maritime climate. This gets air heated from land.
Excuse me, I think we're also, or I at least am still seeing the phase changes slide. Is that what you're on?
Phase change slide. Which one are you?
20.
Which slide number?
20.
20. Okay.
Yeah, you're frozen at 20.
Well, you know, this is a good place to stop. I was only going to go to 25 today. So we'll pick right up at 20 next class, and I will get to the techies and have them fix the computer. I was only going to go to 25. So on Wednesday, we'll pick right up on number 20. I thank you guys for your patience. I greatly appreciate it. Please get your quizzes done and get those current events in Wednesday, or that's Wednesday night. I look forward to seeing all of you on Wednesday with an updated computer. Thank you, everybody. Have a great day.
Thank you. Have a good one.
Thank you.